Hi everybody, welcome to a new tutorial. This is the second video of the Machine Learning from Scratch tutorial series. In this series we are going to implement popular machine learning algorithms using only built-in Python modules and NumPy. Today we are going to implement the linear regression algorithm. So let's talk about the concept of linear regression first. So in regression we want to predict continuous values, whereas in classification we want to predict a discrete value like a class label 0 or 1. So if we have a look at this example plot, then we have our data, the blue dots, and we want to approximate this data with a linear function. That's why it's called linear regression. So we use a linear function to predict the values. So we can define the approximation as y hat equals w times x plus b. So this is a line equation where w, or our weights, is the slope and b is the bias, or just the shift along the y-axis in the 2D case. So this is the approximation, and now we have to come up with this w and the b. And how do we find this? So for this we define a cost function, and in linear regression this is the mean squared error. So this is the difference between the actual value and the approximated value. So the actual value, for this we need training samples, and then we square this difference and sum over all the samples and then divide by the number of samples. So this way we get the mean error. This is the cost function of so this is the error, and of course we want to have the error as small as possible. So we have to find the minimum of this function. And how do we find the minimum? So for this we need to calculate the derivative, or the gradient. So we calculate the gradient of our cost function with respect to w and with respect to b. So this is the formula of the gradient. Please check this for yourself, and I will also put some links in the description with some further readings, but I will not go into detail now. And now with this gradient we use a technique that is called gradient descent. So this is an iterative method to get to the minimum. So if we have our object or our cost function here, then we start somewhere. So we have some initialization of the weights and the bias. And then we want to go into the direction of the steepest descent. And the steepest descent is also the gradient. So we want to go into the direction of into the negative direction of the gradient. And we do this iteratively until we finally reach the minimum. And with each iteration we have a update rule for the new weights and new bias. So the new w is the old w minus alpha times the derivative. So minus because we want to go into the negative direction. And then this alpha is the so-called learning rate, and this is an important parameter for our model. So the learning rate defines how far we go into this direction with each iteration step. So for example, if we use a small learning rate, then it may take longer, but it can finally reach the minimum. And if we use a big learning rate, then it might be faster, but it might also jump around like this and never find the minimum. So this is an important parameter that we have to specify, and please keep that in mind. So now that we know our update rules, I've written the formulas for the derivatives again here, and then simplified them a little bit. Please check that for yourself. So these are the formulas for the update rules and the derivatives, and this is all we need to know. So now we can get started. So now let's define a class called Linear Regression. And this will, of course, has an init method, or double underscore init. And then it has self, and it gets the learning rate, and I will give this a default value. So usually this is a very small value, so I will give it 0.001, and then I will give it a number of iterations, so how many iterations we use in our gradient descent method. And I will also give this a default value, so I will say this is 1000. And then I will simply store them here, so I will say self lr equals lr, and self n iters equals n iters. And then later we have to come up with the weights, but here at the beginning I will simply say self weights equals none, and self.bias equals none. And then we have to define two functions, and we will follow the conventions of other machine learning libraries here. So we will define a fit method, which takes the training samples and the labels for them. So this will involve the training step and the gradient descent. And then we will define a predict method. So then when it gets new test samples, then it can approximate the value and return the value. So these are the functions we have to implement. And before we go on, let's have a quick look at the data x and y. So how does this look? And for this I've written a little example script, and I used the scikit-learn module to generate some example data. And I will split the data into training and test samples, and also training and test labels. So first of all, let's have a look at how this data looks. So here is the plot. So this is how our data looks, and now we want to find a function somewhere here that approximates the value. And let's have a look at the shape of our x and y. So let's run this, and no, I don't want this plot here anymore. So if we see that our x is a ND array of size 80 by 1, and this is because I put in here I want to have 100 samples and one feature for each sample, and then I will split this so our training samples only has 80 samples in it. So this is a ND array of size 80 by 1, and our training labels is just a 1D row vector of also of size 80. So for each training sample we have one value. So this is how our data looks, and now let's continue. So let's implement the fit method. So as I said, we need to implement the gradient descent method here, and the gradient descent always needs to start somewhere. So we need to have some initialization. So let's init our parameters, and for this first let's get the number of samples and the number of features. And we can get this by saying this is x.shape, and then we simply initialize all the weights with 0. So we can say self weights equals NumPy zeros of size and features. So for each component we put in a 0, and self.bias equals 0. This is just a value. So you can also use random values here, but 0 is just fine. So let's use 0 here. And then we use the gradient descent. So this is an iterative process. So we use a for loop. So for I or actually we don't need this, so for underscore in range and then self.nIters. And now what we need, we first have to approximate, or let's have a look at the formula again. So the formula for our new weights is the old weight minus the learning rate times the derivative. And the derivative with respect to w is 1 over n. And then we have the sum, and the sum over 2 times xi times, and then the difference here of this approximated and the actual values. So let's first calculate this approximation. So we have this formula here. The approximation is the weights times our x plus the bias. So let's do this. Let's say, and let's call this y predicted equals, and then we can use np dot and then x and self dot weights plus bias. So this will multiply the x with the weights. And now that we have the approximation, we can calculate the derivative with respect to w. And this is, let's again have a look at this formula, 1 over n, and then the sum, and then inside the sum we have the product of x times this. So we say 1 over n samples, so we already got the number of samples here, and then times, and then we have the sum product, so this is nothing else but also the dot product, so np dot, but now we have to be careful. So what we did here, here we multiply each weight component with the feature vector component and sum it up. And we do this for all samples and then get one value for each sample. And here we want to get one value for each feature vector component. So we multiply each sample with the predicted value and sum it up. So, and then we do this for each feature vector component and get one value for each component. So this is the other way around. So this is along the other axis, and we can, so we have to use x dot transposed here, x dot t, and this is the dot product of the transposed x, and then we have y predicted minus the actual y. So please check the NumPy dot function for yourself. So this is the derivative of the w, and the derivative of the bias is also 1, or again let's have a look at the formula. So this is the same except that we don't have the x here. So this is 1 over n and then just the sum of this difference. And by the way, I left the 2 out, so this is just a scaling factor that we can omit. So here 1 over n and then the sum over the difference. So again 1 over number of samples, and then we can say numpy.sum, and the sum of y predicted minus actual y. So these are our derivatives, and now we update our weights. So we say self weights minus equals self dot learning rate times this derivative, and self dot bias equals self minus equals self dot learning rate times the derivative. And yeah, so this is the gradient descent. And now we need the predict method. So again, we approximate the values with this formula. So we already have this here. So this is the dot product of x and the weights plus the bias. And then we simply return this. So this is the whole implementation that we need. And I forgot to import NumPy, of course. So I say, let's say import NumPy S and P so that we can use this. And now let's test this. So let's import this class. So let's say from linear regression, import linear regression, and then create some regressor equals linear regression. And then we say regressor.fit, and we want to fit the training samples and the training labels. And then we can say we can get predicted values equals regressor.predict. And now we want to predict the test samples. And now in order to calculate or to see how our model performs, now we can't use the accuracy measure, but here we use the mean squared error. So as I said, this is our cost function, the mean squared error, that tells us how big the difference between the actual value and the approximated value is. So let's define the mean squared error. Let's say def MSE, and this will get the actual values and the predicted values. And this is the NumPy. Here we can use NumPy mean, and then simply the difference to the power of 2. So y true minus y predicted to the power of 2. And then we want to return this. So let's see, or let's say MSE value equals MSE of y test and the predicted values. And let's print this. So now if we run this, see, it's not running, bias is not defined. So let's say what did we miss here, self.bias. And let's run this again. So line 27. Oh, sorry, I copied this and forgot this here too. So next try. Now we see that our performance, so the mean squared error is 783, so this is pretty high. So let's use another learning rate here. So let's say LR equals 0.01. And let's run this. And now we see that our error is smaller. And let's actually plot this. So let's plot first with the original learning rate. Let's see how the plot looks. So now our plot looks like this. So it's almost like the the right slope, but not exactly. And now let's have the other learning rate. So let's use this learning rate and let's run this. And now our plot looks like this, and this looks pretty good actually. So this is a pretty good fit or pretty good approximation of this data with a linear function. So we see that our implementation is working, and I hope you enjoyed this tutorial, and see you in the next tutorial. Bye.